Well, let's see. We're asked to find all the divisors of 650. So, well, we could just start listing them. We know that 1 times 650, those are two factors of 650. We know it's an even number, so we can divide it by 2, and that gives us 2 times, what, 325? Let's see. Ends in a 0, so it's divisible by 5. So that gives us 5 times what? 130. Let's see, what else? Well, it's obviously divisible by 10, so 10 times 65. Let's see, any more? Let me think. Well, it sure would be nice to have a way to be able to know how many you're looking for, right? So that you know when you're done. If we knew, for example, that we were looking for, say, 8 divisors of 650, then we'd know now that we're done. But I don't know at this point how many divisors we have of 650. So what I'm going to teach you is a little trick to figure out how many divisors a number has. And it's based on something called the fundamental principle of counting. Sounds like a really important principle, obviously, if it's called the fundamental principle of counting. You might know it as the product rule. And what it says is pretty basic. It basically says if you have, let's say, n ways of doing one thing and m ways of doing another thing, then you can just multiply n times n, m times n or n times m, to get the number of ways to do the combination of the two things. Okay. So for example, let's say I have 2 pair of pants, and let's say I have 3 shirts. Then if I want to know how many outfits I can create, so I mean all these pants are different and all these shirts are different. If I want to know how many outfits I can make, I can just take 2 times 3, because I have 2 choices for pants and 3 choices for shirt. And once I have a pair of pants and a shirt, I've got an outfit, basically. So, and you can see that in the tree. If I show my 2 options, maybe I have jeans, and let's say I have khakis. Khakis. Alright, those are my 2 choices for pants. And maybe I have a red shirt, and let's say I have a yellow shirt, and let's say I have a blue shirt. Okay, so if I choose the jeans, I have 3 choices for shirt, and if I choose the khakis, I have the same 3 choices of shirt. Okay, I don't have anything clashing, so the choice of shirt is not dependent on my choice of pants. Okay, maybe if I had a pair of purple pants, maybe I wouldn't want to wear them with a red shirt. I don't know. Depends on what your taste is. Okay, so you can see how we end up getting 6 outfits, and these basically show you all the possible outfits. We get the jeans with the red shirt, jeans with the yellow, jeans with the blue, or the khakis with the red, khakis with the yellow, khakis with the blue. Alright, so let's go back to this finding the number of divisors of 650. And it depends on being able to factor 650 into its prime factors. And you may have done a factor tree before. We can factor this into 65 times 10, and we can factor 65 into 5 times 13, right? And 10 factors into 2 times 5, all right? And now all of these numbers here are prime. So the prime factors of 650, if I write 650 in terms of its prime factors, I get 2 times 5 squared times 13. Okay? So those are the prime factors. And all of the factors of 650 are some combination of the prime factors of 650. Okay, so the factors of 650 are made up of these prime factors. Okay, 13 is obviously a factor. It's also a prime factor. I can take 2 times one of the 5s, and that's a factor. I can take 5 times 13, and that's going to be a factor. I can take 2 times 13, that's going to be a factor. So I can create different combinations of these prime factors, and that will give me all the factors of 650. So the question is, how many ways can I put together these prime factors in order to get all of these divisors? I guess I'm using divisor and factor interchangeably, but these are the prime factors. So how can I use these prime factors to create combinations that give me all the divisors of 650? All right. So here's the trick. A divisor of 650 can either have no 2s, 0 2s, or it can have, I'll write the options down here. We can have 0 2s, or we can have 1 2. Okay, those are our choices for the power of 2. So 2 to the 0 is just 1. That just means that it doesn't have any factor of 2. Okay, and if it has 1 2, that's so 2 to the 0 is 1. So that means we have no 2s, and 2 to the 1 is 2. That just means we have 1 2. Okay, and our choices for the factors of 5, we can have no 5s, we could have 1 5s, or we could have 2 5s. Okay, so we have actually 3 choices for the for how many 5s are in our divisor. And then for 13, that's just we can either have 0, we can have no 13s, or we can have 1 13. Okay, so basically we have 2 choices for how many 2s to include in the divisor. We have 3 choices for how many 5s to include in the divisor, and we have 2 choices for the number of 13s to include in the divisor. Okay, and if we come up with all those combinations, we'll get it. So you can see we have 2 choices for the number of 2s, we have 3 choices for the number of 5s, and 2 choices for the number of 13s, which should give us 12 divisors of 650. So obviously I only have 8, so there's a couple missing, right? And let's take a look at what the tree would look like for all the different options of 600 for all the different divisors of 650. Okay, so basically here's our choices. We have a factor of 2. We can either have 1 2, or no 2s. Do you see? And the power of 5, we can have no 5s, we can have 1 5, or we can have 2 5s. And independent of how many factors of 2, we still have 3 choices for the power of 5. Okay, that just tells us how many 5s we're including in that divisor. Okay, and then again we have 2 choices for the number of 13s to include in the divisor. And here are all the factors. If you multiply that out, if you trace through any branch of the tree, you'll get a unique divisor of 650. Okay, so for example, this branch, let me use a highlighter. This branch, this tells us we have, here's a highlighter, we have no 2s, we have 2 5s, and we have 1 13, which gives us 325, which is one of the divisors of 650. If we look at another case, here we have 1 2, we have no 5s, and we have 1 13, which gives us the 26. Okay, so each one of those branches on the tree is going to give us a unique divisor of 650. Alright, so there's the general rule for any number. If we want to know how many factors it has, we need to first of all, here's the steps, let me write them out. So the first step is to write the prime factorization. Okay, so we look at the prime factorization, and then we look at the exponent of each prime factor. Exponent of each prime factor. And we have to account for the fact that 0 is an option. So if we have, say, 7 cubed in our prime factorization, then we can have 0 sevens, we can have 1 or 2 or 3 sevens, so that gives us 4 options. So we need to add 1 to each, so let's see, add 1 to each exponent and multiply. And that will give us the number of factors that divisors that number has. So here is the rule written in mathematical notation. So if we have n and we write it in terms of its prime factors, then the number of positive divisors that number has is essentially the exponent plus 1 times the next exponent plus 1 times the next exponent plus 1. So you just take all the input exponents, add 1, and multiply. Okay? So let's do another example. Alright, let's look at this one. This is a lot harder. We want to find all the divisors of, we can leave this up here just so for reference, of 7,497. Yeesh. Okay. Well, the hardest part of this one is just finding the factors, the prime factors. So I know it's not divisible by 2 because it's not even. Let's check 3. I have 11 and 16, which gives us 27. That's the digit sum. And 27 is divisible by 3, but it's also divisible by 9. So I know this number is divisible by 9. So I can actually take care of 2 3's by dividing this number by 9. Okay, so what do we get when we divide by 9? Well, we get, let's see, that's 3, 27, 27. That gives us 833. Okay, so the first 2 factors are 9 and 833. Okay, and then this is 3 times 3. So there we have that part of it down into prime factors. Now let's look at 833. That's not an easy one either. It's not divisible by 2. It's not divisible by 3 because the digit sum is 14, and that's not going to work. It doesn't end in a 0 or 5, so it's not divisible by 5. So let's try 7. Let's just try this out. 833, if we divide it by 7, we get, let's see, 1, 7, 13. Let's see, I guess I just can do a 1, 7, and then I'm left with, what, 63 and 9. Oh, so good. It's divisible by 7, and it's 7 times 119. Alright. Well, now we know 119 is not divisible by 2 or 3 or 4 or 5, again, because this 833 was not divisible by any of those numbers. So let's try 7 again. Alright, 7, 119, let's see, 7, that gives us 49. Ah, look at that. Hey, so this is 7 times 17. Alright, and we know 17 is prime. So our prime factorization is, and again, like I said, this is the hard part, 3 squared times 7 squared times 17. So how many factors do we have of 7,497? We have 3 times 3 times 2 is 18, right? So we have 18 factors of, or we could say divisors of 7,497.